Okay, so in this video I'm going to derive the 5 SUVAT equations. Now the SUVAT equations are also known as the constant acceleration equations, and this is because they only apply when the acceleration is constant. Now I did touch on very briefly in the last video that the acceleration is equal to the gradient of a velocity time graph. Now if you want the acceleration to be constant, it means then the gradient of the velocity time graph must be constant, i.e. it must be a linear graph. Okay, constant gradient. So I'm going to derive the 5 SUVAT equations from this graph, which is just a general linear velocity time graph. It's got some y-intercept or vertical axis intercept, which I've called u. It's got some gradient, which is positive, but the equations will work if it's negative. It's not a problem. V is some velocity when time is t. Okay. So what we have is the gradient is going to equal the acceleration. And the other thing I touched on last video was that the area under a velocity time graph is equal to the displacement, which means that the area of that shape is equal to S, which is the letter used for displacement. They're called the SUVAT equations because the 5 letters that are used are S, U, V, A and T. S is the displacement of the object at time t. U is the velocity of the object at time 0, which is essentially also known as the initial velocity. V is the velocity of the object at time t. A is your constant acceleration value. And T, that is your variable. That's the one that changes and affects everything else. Okay? The time variable. Okay, so it's going to use those 2 bits of information. The acceleration is the gradient, and the area is the displacement, to calculate 2 equations. So the acceleration is the gradient. So the gradient of a linear graph is the difference in y, or difference in the vertical, divided by difference in the horizontal. So the difference in vertical there is going to be the v value minus the u value. And we're going to divide that by the difference in the horizontal, which is from 0 to t. So therefore the difference is t. Rearrange that, we're going to get at is equal to v minus u, and then therefore v is equal to u plus at, and that's my first SUVAT equation. The second one is going to come from the fact that the area is equal to the displacement, so I'm going to do this one in red. So the area is equal to the displacement, which is S. So S is going to be equal to this area, but this area is the area of the trapezium. So the formula for the area of trapezium is the sum of the 2 parallel sides divided by 2 times the perpendicular distance. Okay. So the sum of these 2 parallel sides is going to be u plus v. The perpendicular distance is t, and we need to divide that by 2. So that's going to be a half into u plus v times t. Okay, and that is my second SUVAT equation. So those 2 are taken from this linear velocity time graph. Next one, what we're going to do is we're going to take these 2 equations and we're going to eliminate each unknown at a time. So first I'm going to eliminate v to give me another SUVAT equation, then I'm going to eliminate u to give me a 4th SUVAT equation, and finally I'm going to eliminate t to give me the 5th and final SUVAT equation. There are 5 SUVAT equations because each equation will omit one of the 5 letters. Okay, S, U, V, A, and T. Okay, so first I'm going to eliminate v. So what I'm going to do is I'm going to take this definition of v as u plus at, and I'm going to dump it straight into here. So it's going to be S is equal to v, but it's going to be written as u plus at. Oh, sorry, that should be a plus. There you go. Apologies. Times t, all divided by 2. No. Start again, sorry. S is going to be v, which is u plus at, plus u. That then gets times by t, and that's all divided by 2. That's looking better. So I can rewrite that as being 2u plus at times t, all over 2. And now I just need to simplify that. So this implies then that S, well, I'm going to get 2ut divided by 2 The 2's are going to cancel, so I'm just left with ut. And here I'm going to get a times t divided by 2. So that can be written as a half at squared. And that's my third SUVAT equation. S equals ut plus half at squared. The fourth one comes in a very similar manner to that one, except instead of taking this definition of v and putting it into here, I'm instead going to rearrange this to make u the subject and then put it into here. So I'm going to get s is equal to v plus u, but I'm going to write u as being equal to v minus at. Okay. U is v minus at. That then gets times by t and divided by 2. So that's going to be 2v minus at multiplied by t, all divided by 2, and then a little bit of simplifying. 2vt divided by 2 is just vt. Oh, there we go. Sorry, 2vt divided by 2 is just vt, and then I've got minus a times t squared over 2. So it's going to be minus half at squared. It's very similar to this one, except instead of a u I've got a v, and instead of a plus I've got a minus. Okay, that's the answer there. Okay, this third one then, a little bit trickier to derive, but not too much of an issue. Let's just remind ourselves of the two SUVAT equations that we got at the beginning. So we got v is equal to u plus at, and s is equal to v plus u divided by 2 multiplied by t. And what I'm going to do is I'm going to take this definition of t, which is going to be v minus u divided by a. Okay, so I minus the u, I divide by a to give me v minus u over a. I'm going to put that definition of t into there to give me a SUVAT equation with no t in it. So that's going to give me then that s is equal to v plus u over 2 multiplied by t, which is v minus u over a, and then I just need to neaten that up. So the top is what's called difference of squares, so it's going to be v squared minus u squared. Okay, because the uv and the minus uv will cancel, and I'm timesing two fractions together, so I can just times their denominators to give me 2a. A little bit of neatening up. That's going to be 2as is equal to v squared minus u squared, and then finally add the u squared, I get v squared is equal to u squared plus 2as, and that is my fifth and final SUVAT equation. Okay, so those are the derivations. You do not need to know those 5 derivations for the course. I just think it's very good to see where they come from, rather than just have the 5 formulae thrown at you. But that is indeed where they come from, and they all are stemmed from the assumption that the acceleration is constant. They only work if the acceleration is constant. Variable acceleration is something that is studied later on in year 12. Okay, so these are the 5 SUVAT equations. In fact, on the new course, you don't even need to learn those. Those 5 are given in the formula book. But these next couple of videos, we will be looking at using the SUVAT equations to solve problems. And just a quick reminder as to what these 5 letters are. S is the displacement at time t. U is the initial velocity of the object. V is the velocity at time t. A is the constant acceleration, must be constant. And t is the time. Thank you for watching.